Hello, everyone. This is the third in a series of lectures covering Chapter 36. Today, we're going to talk about images formed by refraction. So, we have already seen how when we look at the light that gets reflected off from an object into a mirror, the image is formed wherever those reflected rays appear to converge. For light that goes through into a new medium, though, it's also going to create an image. This image that, again, it's a refraction of the light coming off the object, forms wherever the refracted rays meet inside the new medium. So our basic setup is going to be this interface here between the two mediums, and it's going to be curving outwards with a radius of curvature equal to r. The distance p between the object and the new medium is just the distance towards the very edge of the interface. And for this example, the assumption is that, first off, that the mediums are transparent so that they easily transfer light through. But specifically for this one, we assume that the incident index of refraction is lower than the one where the light rays refract through, though a lot of the derivations for this section will still work out the same, even if you're going from a higher index to a lower index. So, quick quiz right off the bat. The question is that you have this object some distance away from the refracting surface, and it starts off from very far away. So imagine point O here all the way to the left edge of the screen, and then you move it towards where it is now, so the distance p decreases. The question is what happens to the image that's being formed inside the refracting surface. So this might be hard to see without motion, but as you bring the object closer to the surface, the rays actually hit further parts of the mirror, so they converge farther away from the edge of the surface. In other words, the image forms farther and farther to the right. Eventually, though, as the object does get closer to the surface, the image is eventually infinitely far away on the right side. But then as the object keeps moving to the right past this point, the image will actually appear on the left side of the surface and slowly creep towards the right to eventually actually catch up to where the object is once the object is right at the interface. So the image starts off moving to the right, and at some point it reappears far away on the left and moves towards the right, towards the surface. Now, we've seen the lens formula here, which is actually similar to the mirror formula that lets us find where the image of an object reflection is going to show up. So for a refracting surface, to figure out where the image will form, we need to take into consideration the indices of refraction of both media as well as the radius of curvature of the surface. Knowing all that and using Snell's law to relate the angle of incidence and refraction, you can derive a formula that's similar to the mirror equation, but now will tell you the location of the refracted image. Also, with a bit more of geometry, you can find the vertical magnification of the image, so how much it, how taller or how shorter it seems after being refracted, by taking the ratio of the first index times the image distance divided by the second index. So the second index again is the one where light gets refracted into times the object distance. And then there's a negative sign because the object, if it's projected inside the second medium, it will end up upside down. So much like a mirror equation, you have to be careful with the signs on each distance. So the distance b for a single refracting surface, like a single mirror, is going to be positive since it's in front of the surface. We call that a real object. The image location, if the refracted rays actually converge at the back of the refracting surface, so in the second medium, then we're actually going to have a positive image location. So Q is positive if the rays converge on the other side of the surface. This is the opposite of what we've seen with mirrors, where Q was only positive if it appeared on the same side as the object. But in this case, if the light actually passes and converges inside the surface, then Q will be positive. If the rays actually don't converge inside the surface, but actually appear to converge from the front of the surface, then that'll be a virtual image. So if the image is on the same side as the object, the image location will actually be negative, despite the object location still being positive. The image height is positive for a upright refracted image, and it's negative when the image is inverted. The radius of curvature is positive when the center of curvature is in the back of the surface, and negative when the center of curvature is in the front of the surface. So in the example we've seen, the surface of refraction is dented outwards, and then the radius of refraction, as drawn here, points inside the surface, points to the right side of the surface. So R will be positive. If the surface here, instead of being dented outwards like this, was dented inwards concave, then the radius would be drawn in front of the surface and it will be negative. This takes some practice, so with a few problems, you can get the hang of what sign goes where. Now, a concave mirror, if you recall, that it'll generally converge light rays. Light rays will reflect in such a way that they'll kind of converge through the central axis. Now, when we have a reflecting surface like this one, as shown in figures A and B, you can actually get a similar situation to the concave mirror where both real and virtual images can be formed. It just depends on whether or not the object is far away or close to the surface. So if the refracted image, again, in figure A, you see a real refracted image where the refracted light rays converge behind the surface where the second medium is. So that's a real image. The second one shows you a virtual image where the image is on the same side of the object. The refracted rays don't actually converge, but appear to converge on the first medium. So there's actually a sweet spot similar to the focal length of mirrors. This is a particular spot where, as the object gets moved from far away to closer to the surface, the image is eventually infinitely far away to the right. And then if you keep moving the object past this point closer to the surface, the image will reappear on the left and catch up to the object. So if we go back to the refraction surface formula and look at this situation where the image is infinitely far away to the right, you can actually get a formula for the distance at which this happens, where the object has to be for its image to be infinitely far away to the right. And this point here depends on the indices of refraction of the two media and the radius of the mirror, the radius of the surface. And this, again, is something similar to the focal point for a mirror. Now, at this sweet spot, if the object is moved farther away from the surface, like in figure A, then the image will appear on the right side of the surface, so behind the surface in the new medium N2, and thus its virtual image. But if P is right at the sweet spot and you move it closer, so towards the surface, so P gets smaller, the image will appear on the left side of the surface, in front of the surface, and so you'll have a virtual image. Now, if you have the case where now you're refracting from a medium with a higher index of refraction than the other, that's going to change things a bit. So in this example, we are now seeing an image start off from a medium with a bigger index of refraction than the medium it's refracting into, so from water to air. And in this case, the formula still works. You can use the same refraction formula to figure out where the image is going to form. And it turns out that when light is refracting into a medium with a lower index, like air, the image that's formed is always on the same side as the object. So if you're above a swimming pool, maybe just walking by the side of the pool, maybe trying to get your towel or something, you look into the water, everything in the water is a refracted image, right? You don't really see things, right? Because light from underwater gets refracted as it travels out of the surface into the air. And everything you see, though, is a virtual image of everything under the pool, under the water, because all the refracted light rays bend away from the normal, so everything appears to emerge from the water, and thus it's in the same side as the object. Therefore, when the new medium you're refracting to has a lower index of refraction, the image is always virtual. So it's kind of like a convex mirror, where a convex mirror, right, diverges light, so no matter where the object is, the image is always virtual. Now, if you look at the formula for finding the position of the image, right, there's a term to account for the curvature of the surface. If the surface is flat, that's the same as having an infinite curvature. So the formula for finding the image location becomes a lot simpler. It's just a ratio of the indices of refraction times the object distance, and then a negative sign that accounts for whether the image will be real or virtual. Now, in the case where you're refracting to a medium with a lower index of refraction, the refracted rays will fan outwards, like in the figure here shown on the right. That means that the image, will be virtual, but actually will appear to be a lot closer to the surface and the object. If it's the other way around, if you're going to a lower index of refraction, if you're going to a higher index of refraction, the refracted rays will be more bent than the incident rays, so the image will appear to the left of the object. So in this figure, we have the image to the right of the object, but if the indices were swapped, the image will be behind the object. So right now, I is to the right of O, but if the indices were the other way around, I will be to the left of O. The image will be formed to the left of the object. So the question is, what happens to the image as the object moves towards the right-hand surface of the material? So it is where it is in the picture, but you're saying that you're moving the object to the right. And what's happening is that no matter what, though, since light is refracting onto a medium with a lower index of refraction, the image is always virtual. So the light rays also fan away, so the image always appears to come closer to the surface and the object. And you can kind of picture that if you kind of see picture O moving closer to the surface, the rays will be fanned out even farther away. The refraction would be a much bigger angle, so the image would still appear closer to the surface than the object. Anyhow, that's all for now. We are going to talk about the thin lens equation next time, so hope to see you then.